11 international conference papers, and 1 book chapter in these research areas. Sir also has funded projects by SERP in his research areas. I extend my heartfelt invitation to Dr. Chandramohan Garu to share his invaluable knowledge. Welcome, sir. Thank you.
Thank you, Vasanta ma'am. Thank you for your introduction. Thank you, Dr. Professor Sadanandam sir, for inviting me for this talk. So with this, quickly, you please stop sharing, ma'am. I'll share my screen. Yeah.
Yes, sir. I have stopped, sir.
Okay. Is my screen is visible?
Yes, sir.
Okay. I made it full screen. Good evening, participants. According to this FTP advancements in artificial intelligence and ML for modern engineering solutions. So I have 2 sessions. Actually, I have to take this session yesterday itself due to some adjustments. Another resource person took, and I'll take 1 session now. Tomorrow, 2 p.m. another session. I'll take it. So in this 3 hours of session, I'll try to cover. Outline. If you see my presentation, I hope my screen is changing the slide, right? Outline is it visible, outline?
Yes, sir. It is updating.
Okay. Yeah. So in this, I'll cover convolution neural network and some applications. Simple, not convolution neural network. I'll cover explainability in convolution neural networks and the interpretability in CNN. This topic I'll cover in this session. Next session, I'll cover recurrent neural networks, if possible, graph neural networks also. Little advancements. All the participants, I'm just requesting how many people know convolution neural network. Please raise your hand in this. I can understand. So total, how many participants are here? Total 108 participants are here. Please raise your hand. How many persons know CNN? So yeah, only 2-3 people. So then I'll start from scratch. Yeah, I'll try to satisfy all the participants. I'll start from scratch. Only 4-5 raise their hands. Thank you very much for your response. So majority people don't know convolution neural networks. I'll start from scratch. I'll cover advanced topics also. Okay. So before going to understand the convolution neural networks, first we should understand what is neural network, how it evolved. Quickly, I'll introduce it. Neural networks like evolved from biological neurons. So what are biological neurons? How biological neurons work? So suppose the nerves signals in our body, humans or any living organisms, signal will go to brain in various ways. Through DNA, it will go, and through nerves, it will go. Through blood, it will pass. Yeah, different signals will go to brain in different way. So those dendrites, we can call it as those various what we can say parameters or various things which will send information to the brain. So those we can call it as dendrites. Here it will process it and it will generate some output. It will send via axon. So this is the biological neuron, how it will work. So biological neuron, we know actually we have sense organs, right? So through sense organs, signals will go to brain. That is exactly like processing unit, like in our computer. So we will give input, it will process it, and it will send output. So suppose simple example, very old common example, I'll take it. Suppose some mosquito is biting on your left hand, imagine. So immediately that pain signal will go to brain. Immediately it will process it in the brain. It will tell output signal, and it will send that output signal to other hand, and it will go and hit that position to hit that mosquito. If it is lucky, it will escape. Otherwise, it will, okay, we can kill that. So here what are mathematics involved? Mathematics involved is from brain, exactly at what distance brain calculates at what distance the mosquito is biting. Suppose if mosquito is biting above somewhere in the shoulder, we can't hit on the hand, right? On the wrist. So if mosquito is biting on the wrist, definitely we'll go and hit that position. So this mathematics is involved. See, all neural networks built on the top of mathematics. So first, when as a fresher, if you start learning deep learning, first you should understand background mathematics. Programming is like just very, very simple, I can say. So if you will not understand background mathematics directly, if you jump to program, it's impossible to understand the deep learning. So that's why I'll always, with my experience, near about 100 FDPs, I took sessions deep learning. So with my experience, mathematical understanding is more important than programming. So that's why I'll explain mathematically. Then I'll go for program. You will understand how easy to understand deep neural networks with the program if you know mathematical background. So now these things are there. By taking this one as reference, we created artificial neural network. So we'll take input and some node it contains. We can call it as neuron. It will process it and it will generate output. So in mathematics, if you say something processing means function. In programming also that we can say function. That function perform particular task. Here also it will do two tasks. First task is linear activation it will do. And another second function, two functions are involved here. Another one is nonlinear activation. So it will do sum up products and it will squash the output. Two things it will do. So neural networks incorporate two fundamental concepts of biological neural nets: neurons, nodes, synapses, weights. We will discuss all those things. Before going to next slide, we should understand another important point. Suppose parallelly how our brain will process is two tasks. Take same mosquito example and take another important example, like something is coming towards your eye. Immediately your eye will take picture of that, it will send to brain will process it and it will send output to the eyes first, close it immediately. Within fraction of seconds it will do. And this mosquito immediately next we will go and hit it. Sometimes parallelly we will do. Okay. But high priority task is this. Okay. So I request all the participants is muted. Otherwise it's a big disturbance for others. So it will process it. How brain decides which task is more prior. Okay. So same way in neural networks also, for particular thing, we will give more weight and particular thing we will give less weight. Where we'll use these neural network? Everywhere, wherever mathematics involved, we will use these deep neural networks. So what are the applications? See, interesting point here is from biological neurons, we created artificial neural network by taking biological neurons as reference. By using artificial network, we will solve biological problems. That is very interesting. What is artificial neural network? So in detailed way, if you go, so here it will take inputs. These nodes takes inputs. It will send those inputs via these links. This is neuron. Input nodes are not neurons. Simply it will take input, it will process, it will send to the link. Each link is associated with some weight. We'll discuss about that weight. What we will see, this input is well known, fixed input, we will send it. So it will do this sigma function says what it is, a vector addition and multiplication task it will do. So what vector addition, multiplication addition, x into double naught, y into double one, z into double two. It will sum up all those values. And this nonlinear activation function squashes that linear function output into some range. Okay. So two functions are there, linear and nonlinear. Okay. One is linear function and another one is nonlinear function. So linear function output is, imagine 4.7. It will squash into that range. So what are the important nonlinear activation functions we use? So those we can say squashing functions. The more very general nonlinear activation functions are sigmoid, tanh and ReLU activation functions. Sigmoid function, mathematical function, you see, mathematically, whatever the Z value, like what we can say, nonlinear, linear function output, it will bring in the range between 0 to 1, in the range between 0 to 1. You substitute any positive, negative value, the output should be between 0 to 1. This red color one shows a sigmoid activation function. See, whatever the negative value, it is giving very small positive function output. For positive values, it is that output is very close to 1. So now tanh function is this mathematical function 1 minus e power minus 2z by 1 plus e power minus 2z. So this blue color line represents the function of this tanh. So for negative values, okay, for negative values, it is very close to -1. For 0 value, it is one. For 0, okay, z is equal to 0. So if you substitute here, we'll understand for z equal to 1, 0 value, it will become 0. The output becomes 0 because this e power 0 becomes 1 minus e power 0 becomes 1. 1 minus 1, 0. And for positive values, it will go up to maximum 1. Another very important activation function is rectified linear unit. So what it will do? So why these nonlinear activation functions means there is a concept in machine learning and deep learning, that is data may be linearly separable, non-linearly separable. Linearly separable means suppose 2 class related data is there. Linearly separable means those 2 classes or data samples we can separate with straight line. Non-linear data means we can't do it as so what we can say on whiteboard, I'll tell you. So suppose this is the data. Imagine this is x and y axis. This is x and y axis. Color I need. Okay. White. Okay. Pencil color. Yeah. So this is one type of data samples. So with a straight line, we can separate these samples and these samples. This we can say linearly separable. These are, we can say, linearly separable. Some samples are there like this. And this is one category. With a straight line, we can't separate it. So for this, we need to do like curved lines. So this type of functions, generating this type of functions are very complex. For that, there is a solution like by using kernel functions. Kernel functions will translate this data into high dimension, where in other dimension. So in that other dimension, maybe we can project it and we can separate those samples. We can do linearly separable in that dimension, other dimension. So just that you keep in mind. So why we are discussing this is rectified linear unit. So these all nonlinear activation functions bring nonlinearity. Okay, it's nonlinear data, nonlinearity for data. These nonlinear activation functions, we can use it. So rectified linear unit, if you take it, negative values, it will make it 0. Positive values, it will keep as it is. So z is less than 0. Function is very simple function. Z is less than 0. It will generate 0. Otherwise, it will keep same z value. Okay. So now I'm going little fast because I need to cover convolutions also. So what is perceptron? Perceptron is a simple neuron, one single neuron. We can call it as perceptron in simple terms. So multi-layer perceptron means multiple neurons we are arranging in the form of layers. MLP is a model of neural networks. So in that, at least 3 layers we will consider. What are those 3 layers? One is input layer, hidden layer, output layer. Based on our application, number of hidden layers, we can increase it. But at least 3 layers. Here we can generate outputs. Output is in the form of activation function output, squashing value. So why we can say this multi-layer feed-forward neural network? So what is feed forward neural network? So information flow in this network is forward direction only. These links are directed links from here to here, from here to here. And feed forward neural networks, fully connected feed forward means for every node to every other node in the next network, there is a link. And another important point, the data flow at input, it will go to hidden, it will go to output layer. And here important point is information is distributed. Whatever the input at all nodes, it will go to each and every neuron in the hidden layer. Whatever the output generated in the hidden layer neurons, it will go to all the neurons in the next layer. Okay. So in this way it will work. Some more important points to feed forward neural network is arranged in layers. Each unit is linked only to the unit of next layer, and no units are linked within the layer. There are no links. Suppose 1 to here no link, there is x2 here no link, and so on. So computations can be processed uniformly from input to hidden to output. No internal state exists. In between input layer to hidden layer, no internal state exists. These are basic properties of feed-forward neural network. Suppose if you want to calculate what is the output this X neuron will generate. First, what it will do, it will sum up products. It will do or vector addition multiplication, sum of vector multiplications it will do. So 1 into 0.25 plus 0.5 into minus 1.5. So it will generate minus 0.5. Some squashing function, I take it 1 by 1 plus e power z. So this value we are submitting. Final output it will generate it. So here also same way it will process it. Here also it will same way it will process it. Finally, each link, again these links also associated with some weights. Again, it will perform this sum of products and nonlinear activation. Finally, it will generate some probability value. Based on that probability value, we will decide this sample belongs to which class, if it is a classification problem. So otherwise, we will do some prediction tasks also. We will discuss later. Now, in this, till now, we discussed these are inputs we will give. How we got these weights, that is the challenging point. So those weights, why weight initialization mechanism is important. Those weights randomly we will initialize. Okay, randomly we will initialize. So in the training process of MLP, we can update these weights. Training of MLP, in simple terms, we can say updation of weights. Proper weights we will adjust. Okay, how to do that through back propagation, we will try to understand. And why weight initialization is very important. So finally, my model is properly identifying particular class or properly predicting some value correctly means it purely depends on the weights, how weights are adjusted. Okay. So initially, randomly, some weights we need to initialize. So if you initialize weights, obviously it is a random process, but we should apply some logic to initialize those random process. So optimization will be achieved in least time. If you initialize weights properly, randomly, the model will converge very quickly. Otherwise, converging to minima will be impossible or it may divergent. What are the weight initialization mechanisms? So there are so many mechanisms. I'll discuss only few here. So what is zero initialization? Suppose how many weights required in this network? So 2 to 3 means 6 links are there, 6 weights required. For each link, 1 weight is associated. And again, 3 to 1, 3 links are there, 3 weights. Total 6 plus 3, 9 weights are required. Okay. So I'll put all weights as 0. But in the forward pass, it will do sum of products and nonlinear activation. Finally, it will generate some probability. In back propagation, we will update weights through back propagation. I'll discuss that later. So to do back propagation, we need to perform some gradient like differentiations. The gradient means loss with respect to loss function. We will do partial differentiation with respect to each and every weight. How weight is influencing that loss. How change in weight can change the loss, that it will say. All that derivative values become same. So it will not learn the model quickly. So that problem will come if you initialize all weights as 0. Random initialization. If you initialize all weights randomly very big, so what will happen? So what will happen? So here, what will happen? Suppose all weights are very big. Here, imagine weights are very, very big values. Here, sum of products becomes very big value. Obviously, if it is very big positive value, the sigmoid function, tanh function, or ReLU function, it will generate very like a positive value. That in that activation itself, I shown you, right? Suppose very big positive value. What it is generating? It is giving very close to 1 probability value. In case of sigmoid also, it is giving very close to 1. If it is tanh, it is giving very big value, whatever the value it is there. So it may lead to some other problem called exploding gradient problem. Whether the input is belongs to class 0 or class 1, due to high weights, it will always says it is a class 1. Okay, it is class 1. If values are very small, like in general way I'm saying, I'm not going in detail way. So exploding gradient and vanishing gradient problem itself mathematically very highly we have to discuss. High mathematics are involved. It will take a lot of time. So I'm giving as an exercise for you. Go to Machine Learning Mastery, and that is a blog. You can search for exploding gradient and vanishing gradient problem. Mathematically, they'll explain very well. So if it is very small values, if you initialize, so obviously very small values, thus any activation function will give very close to 0. Even though if it is a class 1 input, it will classify as class 0. So these problems will come. So then the scientists identified some approaches. One is Xavier Glorot initialization. So Xavier Glorot, what he did, he applied this logic by using network itself. He identified this sigma, that is square root of 2 by fan in plus fan out. Fan in means so the number of links going to particular neuron that represents fan in. It is like in degree and out degree in the graph. Fan out means number of outputs going from that neuron. Okay, so with respect to this, number of inputs in degree, fan in is 2, fan out is 1. Okay, so like that. So we got 2.5 value here. Okay, so between 0 to 2.5 values, you pick 9 random values by following normal distribution. That's the meaning of this function. So if you follow that, definitely your model mathematics, there is a very big association with the distributions. So they brought these formulas. If you pick these weight values in this range by following normal distribution, definitely it will converge. Another formula they generated for uniform also. R value they calculated. R value is square root of 6 by fan in plus fan out. If you get R value equal to minus 1.5 or some more than that, imagine like maybe 3.6 or 3.9, minus 3.62 plus 3.6 range, you just pick number of weights required, number of values for a similar number of weights values, you pick it by following uniform distribution. So this is another technique. Hey, simplified these formulas. That's it. Okay, these are weight initialization techniques. Now, so functions, loss functions, what we use for prediction, like regression problem. Regression problem means, in machine learning, regression means, so we will predict some continuous value. So that continuous value, whatever we predicted, we will measure in terms of mean square error, how the predicted value is similar to actual value. By using mean square error, we will, this is one measure to predict like prediction problems. And for classification problems, we'll use these two formulas. One is binary cross entropy. It is minus y log y cap plus 1 minus y log y minus y cap. Y is actual class label. The y cap is predicted class label. By using this formula, we calculate cost function. And in case of multi-class classification, number of classes, sigma class 1 to m, that predicted what is the predicted score for class 1, predicted score for class 2, predicted score for class 3, what is the this is predicted score, this is actual score. Okay, so based on this we will calculate loss function. With respect to loss only, we will try to adjust the weights. Okay, so now another regularization is there. This we will discuss in further sessions. Now, very simple task MLP we discussed, and how can we update weights through backpropagation? Quickly I'll discuss. Then we will jump into convolutional neural network. So this is MLP, simple MLP. 4 input nodes are there. 2 hidden layers are there. 1 output layer is there. 2 hidden layers. First hidden layer contains 3 neurons. Second hidden layer contains 2 neurons. Output layer contains 1 neuron. So here there are no functions because it is taking input and passing via all these links. So neurons starts from here, means functions starts in this layer. So how we are giving numbering for functions? This is first number F1 represent first layer where function starts. In the first layer, first neuron, second neuron, third neuron. This is second layer. Second layer, first neuron, second layer, second neuron. Third layer, first neuron. In this way, they define function numbers. Output you see, from here output will generate. First from first layer, from first neuron output is generated. OIJ means I layer number, J means neuron number. So here if you see from first layer, second neuron output is generating and so on. If you see this output O21, why I am saying this O21 everything clearly in partial differentiation, all these are useful. That's why I'm taking this O22. Why O22? From second neuron, from second layers, from second neuron it is generated. Third layer, first neuron, this output is generated. This O31 is predicted value. Last binary cross entropy, mean square error, whatever the categorical cross entropy, we can calculate this loss function. Okay. Now what are weights? So say 4 inputs are there. 3 neurons are there. 4 into 3, total 12 edges are there. 12 weights required. Here 3 into 2, 6 weights required. Here 2 weights required. Total 20 weights required. Means initially for all these weights we will give some random values by following any of the approach. But if few people are doing research, we never specify which weight initialization mechanism we are giving. Python automatically in the if you analyze the code, you will understand which weight initialization mechanism they are using. Okay. Now what is backpropagation? These are the weights. Now to perform backpropagation, what we are doing indirectly, we follow some optimization function. By using this optimization function, by following the steps in optimization function, we can update the weights. What this SGD optimization tells us, I'm not going in detail mathematically. So SGD, stochastic gradient descent performs for all n samples this backpropagation, but SGD is stochastic gradient descent optimization. For one sample, it will perform every time. SGD with the batch size K also it will do. So batch of K samples, K input samples, it will do backpropagation. So I'll not go in detail. That initialization of variables, what the SGD tells us, initialize of variables means weights. See, training the MLP model is simply updating the weights, I'll tell you. Okay. So initialization of variables, weights, update rule, what update rule says? Find new weight by using old weight minus eta dou L by dou W power Kij. So we calculate loss, partial differentiation of loss with respect to each and every weight, how this weight is influencing loss. Okay, how this weight is influencing loss. I'll take one simple function, you will understand. That simple function is, imagine this is my x-axis, this is my y-axis, okay, y-axis. this y is equals to f of x. So the function is like this. Okay, like this. For x values, something like that, x1, x2, x3, and so on, x10, x15, take randomly, x16, and so on. So this is my function. The function, this parabola, like x square function. So this is my function. What we will do, dou f of x by dou x16. Okay. If you do, what is the tangent, like slope here with x-axis? Say with x-axis, it's a positive because the slope tan theta within that first quadrant, it is positive. So positive value will get here. Okay. Imagine this is my weight. This is my last function. Okay. So weight Wijk volt. Okay. If it is this direction, actually my target is my function value should be 0. Means, so here my function value at this is here, that here last value is this much. Okay. I want to reduce this last value. To reduce that last value, we should bring this weight. We should reduce this weight. If you reduce these weights, obviously our loss will reduce it. Suppose if my weight value is this direction. Okay, my weight value is in this direction. Suppose x2, imagine here slope. So this is with x-axis, it will do theta. This theta is more than 90. So it will generate negative value. Tan 90 plus value is negative value. So to reduce the loss, this weight I need to increase it towards this direction. So ultimately, what is our goal? We should bring the loss value to close to 0. To bring loss values close to 0, this weight, x2 weight, we should increase it. This x16 weight, we should decrease it. In this way, we can converge. In this way, we can converge. So now, suppose, what is this theta learning rate? It is between 0 to 1. A hyperparameter we will call it, that I'll discuss later. If this value weight is towards this direction, it will generate negative value. What we need to do, if old weight is something, we need to increase that weight. So this value becomes negative. This value is negative plus some positive. It will increase it. Negative value will increase it. If it is this value is right side, positive value, the old value is positive, some value we are reducing it. In this way, we can update weights. So perform what we are performing. So after this, I'll ask questions if you want. I'll address questions. If you have any questions, please type in chat box. I will address those questions later. Now, there is a chain rule in mathematics. What is that chain rule? If x is input, a function is performing some operation on x, and another function performing some operation on this x, and h is another function performing output of f of x and g of x. So to understand what is the change in rate of x will change in rate of this h of x output. So what we will do partial differentiation, dou h by dou x equals to what is the information flow in this direction and what is the information flow in this direction. Both we should understand. So for this, dou h by dou f in this rule way into dou f by dou x plus dou h by dou g into dou g by dou x. This is chain rule we follow. In back propagation, we will apply this chain rule. Now we should just understand this, how to perform partial differentiation of loss function with respect to this these weight, that the weights are going from second layer to third layer. So dou L by dou double power 3 1 1. This how this weight is influencing this loss is equals to dou L by dou O31. Whatever the output generating from this neuron, this weight is influencing this one, and this output. So dou L by dou O31 into dou O31 by dou O21. Okay, sorry, dou this weight. Okay, this weight is influencing loss via O31, right? That's the meaning. And this weight, this W power 321 is influencing this loss via O31. So dou L by dou O31 into dou O31 by this one. Now W power 2 weights means which are going from layer 1 to layer 2. This weight, how it is influencing? This weight is influencing O21. This O21 is influencing O31. O31 is influencing loss. So dou L by dou W power 2 1 1 equal to dou L by dou O31, dou O31 by. Actually, these partial differentiations we have to do. Same way we need to perform partial differentiation of loss with respect to this weight, these weights. This weight influence via in this way, this weight influence via this way. So chain rule we can apply, we will calculate partial differentiation. After performing partial differentiation, we need to update these weights. So when to terminate this process? Perform until till converge. What is the meaning of convergence? Various definitions are there, convergence. So if loss is very, very minimal, then we will terminate this process. Our loss is reached to pre-specified threshold, then we can terminate it. Or the new weight is not at all updating, then also we can terminate it. How we can specify this? So if you come to this previously from 16 update jump to here, then there to jump to here, there to jump to here only, means this changing of weights are very small if you are doing. So this direction also, first it will jump big, next small, big jump, small jump, small jump. Sometimes here it will jump here itself. So ideal case only it will go to 0. Usually it will not go to 0, ideal case only. After that, after some duration, after some epochs, it will not change much. So there we can terminate it. This is about back propagation. Till now, any questions? Then I'll go to convolution neural networks. Any questions in chat box? Sir, how to set the weights initially for a different data set of different domain? So there is no specific mechanism domain to domain. Yeah. So in case of MLP, we follow any one of these weight initialization mechanisms. So we can set the values randomly. Later, it will automatically update the weights. How can we understand the source of error propagation? Source of error propagation. Source of error, see, in the forward propagation, how we are calculating predicted value based on inputs and based on weights. Okay, so we are doing like supervised learning, because whatever the input is there, class labels are there, or like if it is a regression problem, and dependent variable values also there. So first, in forward propagation, for all the samples, we will predict values. Yeah, I'll explain here. Suppose in the training process, this is my model, MLP model. In the training process, I'm sending my inputs, 100 inputs I'm sending. For these 100 inputs, imagine these 100 samples. Input is different, sample is zero. For 100 samples, corresponding class labels are there. So those class labels, we can say Y value. Suppose if you give this input to this model, it will predict some value. For these 100 samples, we will get some 100 values. Those we can say predicted value. Okay. So initially in the first propagation, in the first forward propagation, we'll predict these values. Now we will compare with actual values with respect to loss function, cost function. Okay. So we got more loss. Okay, how we got more loss? What is the, because input we will not change, only learnable changeable parameter is weights. We will try to change weights in such a way that there is a logic we are applying in optimization. What is the logic? How this weight is influencing. Just 1 second. Hello. Yes, I am going tomorrow morning. Yes, I informed to coordinators and they are sending car tomorrow morning 5 a.m. Yeah. Sorry. So this predicted these values will get it. So only change the logic how we are changing weights is, if some weight, suppose in this if this weight is increasing the loss, means we'll try to reduce this weight. If the change is this weight is decreasing the loss, means we will increase this weight. That's the meaning. That's why I explained this graph. If weight is this side, we'll try to increase this weight. If weight is this side, we'll try to decrease this weight. Due to that, the loss will reduce. That is the logic we'll apply. And we will update the weights. Next question, quickly I'll take it. I hope you understood this. And sir, is speech to text is related to speech to text? Yeah, NLP only, speech recognition, everything related to NP. Please elaborate a little, like we say something in chat GPT and gets converted text in what. Yeah. So tomorrow on RNNs, when we discuss RNNs, that time I'll take one case study related to NLP. Yeah, thank you. So these many questions only I'll take now. So I have to jump into CNN. So now tell me, what are the problems? Every deep neural network, for every deep neural network, there is a background. There it faces some problems. To overcome those problems, so we will evolve other neural network. So in this one, imagine if you are MLP, this is very small MLP. Suppose if your MLP number of inputs are 1000 neural input nodes. So input nodes, 1000 nodes are there. So first hidden layer, imagine, contains 500 neurons. Okay. Next hidden layer contains 250 neurons, or 200 for simplicity. I'll take it. Next last output layer contains only 10 neurons. Oh, sorry, 10 neurons. Now, how many weights are associated? 5,000 into 500, 5 lakhs. 500 into 200, 1 lakh, 6 lakhs. 200 into 10, 20. 6 lakhs, 2,000 weights are associated. Every forward propagation. So initially we will update these many weights. In backward propagation, we have to perform partial differentiation of loss with respect to all these 6 lakhs weights. All these 6 lakhs weights. Okay. And every time we need to subtract it. If you perform this for 10 epochs, imagine 10 times. If you do this, 6 lakhs into this 10 times means 6 million times we need to update the weights. We need to perform partial differentiation. So this is very hectic. So, and this MLP, the number of total parameters can grow to very high, and it discards the spatial information. Okay, it discards spatial information. CNN and Convnet solve these problems, because CNN is not fully connected. Feed forward neural network, it's like a sparsely connected neural network. CNN, before going to discuss CNN, we should understand what is the difference between machine learning and what is the difference between deep learning. Why so many machine learning models are there? But why we are going for deep learning models? I know few differences. First difference is machine learning, the model performance, training and testing performance purely depends on how features we are extracting, how best features we can extract. So the model performance depends on how best way you can extract features. If you extract the features very effectively, your model will converge very quickly. But some research areas, it's very difficult to extract features. Okay, even domain expert can't extract features properly. So then deep learning can do two tasks. One, features it will extract it, and it will do classification or prediction task. So, and another difference, machine learning, suppose at this moment, at this quarter to 7 and 31st January, I have some data set. So I can train the model. Next February 30, February 27, 28 or 29, we got other data. We need to train another model freshly from scratch. But in deep learning, it's not like that. If you got data now, you can build a model, and the next another data came, you can apply transfer learning, or you can fine tune the model. Okay, not from scratch. Already learned model, we can train it. Transfer learning concept is there in deep learning, and fine tuning concept is there. That is another difference. And the third difference is machine learning, mostly extraction of features for small data is easy. But if it is huge data, big data, it's very challenging to extract features. But deep learning, it needs huge data, then only it will train properly. Okay, these are the major differences usually why we are going. Along with that, so many other differences are there. So that's why we are going for deep learning. It will extract features, and we can do transfer learning. A trained model, we can enhance the model, or a big huge data also we can build model. Yeah, these are the advantages. What CNN can do? CNN simply take fixed length input and it will map to fixed length output. Means it will take fixed length inputs, and it will generate probability values or some prediction score for that input. Okay, so CNN, any neural network, if you take it, we will give input in the form of numerical format only. Whether it is take NLP problems, text problems, images, video, signals, like bioinformatics, DNA sequence, protein sequence, whatever the data, you take it. Okay, in the form of numerical format only we will give. Pre-processing is mandatory anywhere. Okay, so accordingly we will fix the input, and we will fix a fixed size input, so we will send to the model. Okay, now from that fixed size input, yeah, take one simple example. So yeah, so this is my image, simple image. Size is 5 by 5. Okay, that size is 5 by 5. So meaning is 5 rows, 5 columns, values it contains. Okay, 5 rows, 5 columns it contains. Okay, so 25 values it contains. So what are those values? If it is a binary image, 0 or 1 it contains. If it is a grayscale image, pixel values are 0 to 255 it contains. If it is a color image, it is like that. So first channel is a red channel. Next channel is green channel, and third channel is blue channel. Okay, it is like that, 3-dimensional. It is 3-dimensional. So what it contains? 0 to 255 values it contains. This also 0 to 255 values it contains. These also pixel value is 0 to 255. Any one of that 0 to 255. But what is the size of this image? 5 by 5 by 3. 3 means channels. 3 channels it contains. So like this, we can convert into numerical vectors. Then we can do deep learning CNN model. What the CNN model can do, it will extract some features from input. How, which format only, number format only, it will extract features. Okay, convolution layer is this is receive image or DNA or text sequence, video, whatever it is as input. As assign importance to various objects, patterns, or like some regions, signals processing, some regions it will give importance, and which is useful to differentiate one signal from other signal, one image from other image, and so on. Convolution layer is used to extract features like edges, corners, endpoints, patterns in DNA sequence, and so on. CNN achieved state-of-the-art results in various research problems like DNA signal prediction, localization, video, like objects detection in the video, segmentation, like penetration, in roads, pedestrian detection, something different, and segmentation. So many tasks will use it. So to understand CNN, very simple CNN is simple maths involved. We should understand some terms. One is convolution. What is convolution? Sorry, I cannot write properly here that term words. Yes, lack of practice actually. Convolution, pooling. Okay, one is pooling, and next one is strides. Okay, strides, and next one is what is that? Dropout. Okay, dropout. So like this, it's 4 terms we should understand first. Then we can easily understand convolution neural network. What is convolution? The convolution is performed on the input data with the filter or kernel or mask. So input image is 6x6 image. It contains some numbers. We will take a kernel. This is kernel, a small matrix. So this 3x3 matrix. In CNN, these input values are fixed. We can't change those. Only these kernel values are randomly initialized. Okay. If you perform convolution by putting this on the top of here, we will do sum of products only. 3 into 1 plus 0 into 0 plus 1 into -1 and so on. It will generate some features from this data. It will generate some features. So the feature matrix size, we can say convolved feature vector size depends on the input size and the kernel size. What is that output? Convolved feature vector size is, if you perform convolution operation on the top of n by n matrix with k by k kernel, it will generate n minus k plus 1 by n minus k plus 1 output. Okay. So this is about convolution operation. So we can move kernel 1 position. Again, we will do perform operation. Again, we will move 1 position, we'll perform some other operation. Am I audible?
Yes, sir.
Okay.
Yes, sir.
And horizontally, we can move 1 position kernel, we can perform convolution operation. After reaching to the end, we will move vertically 1 position and again horizontal, vertical, horizontal, completely we will do it. Okay. Now, what is padding and what is strides? So we are getting from this big input, we are getting these features. Okay. After first convolution. Now, if you perform convolution, suppose this is a small matrix, 3x3 matrix with 2x2 kernel. If you do it by using previous formula, 3 minus 2 plus 1 by 3 minus 2 plus 1 size convolved feature vector, it will generate. Means only 4 values it will generate. But I need more values. For that, what we have to do? We have to pad. So pad equal to 1 means 1 row up, 1 row down, 1 column left, 1 column right. We can add it. Okay. So now we will perform convolution. It will generate little big convolved feature vector. So if this is the formula, n minus k plus 2p plus 1 by n minus k plus 2p plus 1. So this is 3 initially, 3 minus 2 plus 2 into p equal to 1 plus 1. 1, 2, 1. So 4 by 4 size matrix it will generate. These are important features. Machine don't know what is feature, whether the input contains text, whether the input contains image, whether the input contains signal. It don't care. Only numbers, it will play with numbers. Now what is stride? Kernel is moving, till now what we discussed, kernel is moving 1 position. Sometimes stride value, it depends on stride. Default is 1. Okay, default is 1. Convolution, in convolution, stride default value is 1. So if you want to specify more size also for stride to jump kernel 1 position, 2 position, 3 position, we can do it. So stride n minus k, n minus n on top of n minus n. If you perform k minus k kernel with padding with strides, this is the equation. This is the output of convolved feature vector. Next to max pooling in machine learning, maybe you studied that feature reduction task. Suppose in machine learning, what we will do, we will extract features, right? Feature one, we can say attributes in data mining, features in machine learning, and so on. Okay, FEM. These are features. These are samples. Row wise is sample, column wise we can say feature. This is class label. Okay, something binary means 0, 1, 0, 1, and so on. So if this n value is 100, imagine. So what we will do in machine learning, we'll try to reduce these features. Instead of 100, we'll try to reduce, we'll take only top 10 features, which important features. For this, there are different concept, PCA, LDA, and SVD, so many feature reduction techniques are there. So same way in deep learning, how to reduce features. So I have somebody unmuted, please mute it. So this is my convolved feature vector. Out of 16 values, I need only few important values. For that, we will define one convolved pool size. This pool size is 2 by 2. So there are no values, random values in the pool. But in kernel, we have random values. In pool, no random values. Just we will put that kernel on top of these 4 values. Here we can specify stride also, how to jump kernel, the pool size, how to jump a pool based on strides. By default, stride equal to pool size. Okay. So first I'll put on top of these 4 values. Pick one. In case of max pooling, we'll take maximum value. In case of average pooling, out of 4, from 4, we can take average value. So strides, if will not specify, it will jump 2 positions. Again, from these 4 values, it will take maximum value. Average case, it will take average value, and so on. In this way, out of 16 values, we are picking only 4 top values in case of max pooling. Usually max pooling we use. Sometimes average pooling also we use it. Okay, this is about pooling. What about stride? Suppose stride we discussed. Dropout. What is dropout? Dropout means to avoid overfitting. Overfitting is a concept in machine learning. Overfitting and underfitting. I'll explain overfitting, underfitting. I'll not go in detail. Now I'll explain in simple term. Suppose you given a material to a student. Question and answer. Student by-hearted questions and answers effectively. If you give that question, he will put exact answer in the question paper. But what you did, he changed the question paper. He just twisted the question. That fellow is unable to write because he is simply by-hearted. Okay, if you change a little logic or if you change a little twisted the question, he'll not perform well in the exam. Same way in machine learning, deep learning, models will overfit. Overfitting means model can understand the input very, very well, but it will not do in testing time. Means for new sample, it will not perform well. That is overfitting. Underfitting means the student didn't prepare well, obviously will not perform well. That is underfitting. So to avoid overfitting, sometimes we can drop some values. Drop means some values, some percentage of values, we can drop it. We will make it 0. Okay, we will make it 0. So that is dropping. Drop 0.1 means 10% of values. 10% of 16 values means 1.6 values. Means one value we can make it, we will drop it randomly. Suppose 112, if you drop it, in max pooling, this value become 100. So this average value also, it will reduce it. Okay. Now I'll go to one model. Okay, one model. I'll explain you how that model works. Yeah, just take one simple example. CNN for MNIST handwritten digit classification. And this is well known, a simple basic problem, classification problem. With CNN, we can classify it. So handwritten digit classification problem. What is the handwritten digit classification problem is, so this MNEST is there. The people collected 70,000 images, handwritten digits like this. Some people write one like this, some may write one like this, some may write one like this, some may write one like this also. There are different ways they'll write it. We will train a model. That model, next time when you give handwritten digit image, it will classify it. It will identify that what is there in that image. So simple classification MNIST is that MNIST contains 70,000 images, 28 by 28 pixel images. The image size is 28 by 28. Grayscale images, pixel values is 0 to 255 only. So the task is we need to classify these 0 to 9 numbers into different classes, 10 classes. This is a 10 class classification problem. How to build the CNN model? How to build the CNN model for this? Okay, simply take it. This is one input. Like this, all inputs we will send. So this is one input. We are performing 5 by 5 kernel. We are taking 5 by 5 kernel in the first convolution. So 5 by 5 kernel, 28 minus 5 plus 1 by 28 minus 1 minus 5 plus 1. So it will generate 24 size convolved feature vector. So we'll not take one single kernel. We'll take multiple kernels. Like kernels, number of kernels are depend on your application, 128, 64, 32, 8, like that we will take kernels. Suppose here N1 kernels we took it. For each kernel, 24 by 24 convolved feature vector it will generate. So for N1 kernels, N1 convolved feature vectors, we got it. Pooling we can do. What pooling can do, 2 by 2 pool. Out of 4 values, okay, horizontally and vertically. So the convolved feature vector size becomes 12 by 12. So 2 by 2 means 24 by 2 into 24 by 2. So to 12 by 12 size it will reduce, means 24 by 24 convolved feature vector we are reduced to 12 by 12, means 12 by 12 important features we extracted. So channels will not change. Next convolution, again 5 by 5 kernel we are doing. So padding, valid padding required, everything we will do it. So this one, 12 minus 5 plus 1 by 12 minus 5, 8 by 8 size convolved feature vector, it will generate it. Here we need to understand one logic strongly. So this 12 by 12, 12 by 12 images are there, like convolved feature vectors. How many are there? So many are there. Like how many? N minus 1 are there. N minus 1 are there. So 1, 2, 3, 4, N1 channels are there. Okay. Next time when you take so 5 by 5 kernel, how it will perform, you know. So this 5 by 5 kernel we defined, but indirectly it is 5 by 5 by N1. It will work. Means 5 by 5, it will take it. It will go up to that much depth. It will go. Okay, that much depth it will go. Okay. Out of these many values, it will generate one single value. Means from all these, one kernel, from all these channels, it will generate one 8 by 8 vector. Now if you take like this N2 kernels, N2 channels, it will generate it. Max pooling, this one reduce 8 by 8 to 4 by 4, 8 by 8 to 4 by 4. Now flatten is another layer we use. This 4 by 4 into N2. N2 you just imagine 5. So 16 into 5, 80 values it will generate it. Means this multiple small two-dimensional vectors into one single dimensional vector it will convert. All these 80 values will pass to these 80 nodes. These 80 nodes are, from here we can say dense layers are fully connected layers. From this it will connect to 10 neurons. So what it will do in this neuron, sum of products and nonlinear activation we use it. So here for softmax we are using. So 10 neurons we have, 10 neurons we have. Okay. Each neuron generates linear value Z1, Z2, and Z2 and Z10. Okay, 10 values, linear 10 linear function outputs it will generate. Softmax is a function, activation function, along with sigmoid tan H ReLU. Softmax we use for multi-class classification. For binary classification in output layer, sigmoid we use it. Okay, so this is softmax function is like e power Z1 Zi by sigma j equal e power Zj. Okay, this operation it will perform. So means for each by it will take 10 Z values and it will convert into some probabilities. It will convert into some probabilities. So initially these what class labels 0, 1, 2, 3, these class labels up to 9 will convert into vectors actually. Okay, 0 means one hat encoding vector 1, 0, 0, 9 zeros. So 1 means 0, 1, 0, 0, 0, 0, 8 zeros. 2 means 0, 1, sorry, 0, 0, 1, 0, 0, and so on. Like this will come. Whatever the softmax converted vector, okay, which for which neuron it is generating more probability value, the sum of these probabilities should be 1. Okay, the sum of this probability should be 1. This vector will compare with this vector. Suppose here it generated a big probability that I'll consider as 1, remaining all are zeros. I'll compare with actual class labels. We'll compare with actual class labels and we'll calculate some loss. This is the way it will work. This is the way. Now we will pass all the images in the training process. In backpropagation, we will update it. Okay. This is about simple convolution neural network concept, and we are training the model. In backpropagation, we can update these kernel values. Okay, we can update these kernel values. So now where we can use this CNN? So for medical image analysis also we can do it. What are the image classification? What are the image processing? What are the tasks we can do? Classification, localization, detection, segmentation, all these tasks we can do. Registration we can do. Classification involves predicting the class for one object, like for one image. And localization, yeah, am I audible?
Yes, sir.
Okay. So localization refers to identifying the location of one or more objects. Okay, in the image, suppose car object, we need to identify where it is, bike where it is, like that. Detection means combining those classification, combining these two tasks, localizes and classifies one or more objects in an image. Detection, this we can say. Image segmentation, it will split the image into different parts. Okay, so next registration means like you take CC cameras. One fellow theft our item, bike, imagine he crossed various signals in different locations. They will take pictures and they will bring one conclusion. They will identify that fellow. Okay, so registration is a process of overlaying two or more images from various imaging equipment or sensors taken at different times and different angles from the same scene to geometrically align the images for analysis. Okay, like same what we can say, forensic sciences, we can use it. Medical image analysis. What are the medical images? We have ultra scan, US scan images, X-ray scan images, CT scan, MRI scan, PET scan, retinal scan. So many medical images are there. So these are different medical images. This is brain image. This is also brain. This is also brain. This is also brain. Only this is CT scan image. See, same brain, but in different medical images, in different way it will represented. So one simple task is tumor is there or not in the brain. Suppose this region tumor is there. Okay, we can classify tumor image, non-tumor image. See, CT scan images, just CT scan images. So whether COVID affected, non-COVID affected. Like this, we can do simple classification tasks. Okay. Now we have 10 more minutes time. Actually, I'll go for one simple program. Okay. So before that, I'll go to one CNN task what we did in bioinformatics. I'll explain. So this is a model architecture. What we did here in CNN, in DNA sequences, some signals it contains. Temporarily imagine a DNA sequence contains characters like A, G, G, A, C, C, 4 characters it contains. Sometimes N character, N one more character it contains. A, C, G, T characters. Okay, so those 90 length characters, imagine. So it is a supervised data set. Each sequence label is 0 or 1. Each sequence label is 0 or 1. Okay, so we converted those sequences into one hat encoding vector. Okay, and we took C. Okay, convolution 1D we used here. So it is generated one-dimensional vectors, convolved feature vectors. So total 32 kernels we took it, 32 such channels it generated. Now see, then dropout 0.2 we did, max pooling, kernel size 2, strides. See what we discussed, same all are here. So due to this max pooling, pool size, this pool size 2, that 90 length by 1 convolved feature vector reduced to 45. Then again one more convolution with the kernel size 4 and number of filters 8. This became 42 by 1 vector. How many? 8 vectors. Again dropout max pooling we used, 21 size it reduced. Another convolution we used, 19 by 1, 8 we generated. Max pooling we used, pool size 2, 9 by 1. Total 9 by 1 one-dimensional small vectors, 8 vectors are there. Flatten converts into 75 one-dimensional vector. So we will pass to this neural network. Hidden layer is there with 32 fully neurons. Finally, we represented here 2 neurons, but for binary classification, 1 neuron is sufficient. Only one probability is sufficient. We'll set some threshold. If it is above 0.5, we will assume as 1. Below 0.5, we'll assume as 0. Okay. For understanding, I put 2 neurons, but it's only 1 neuron. How we can do coding part, convolution coding part. Simple example I'll show you. In Google Colab. I think I know other resource person starts the session 7:30. What I can do, 7:25, I'll stop it by showing this code. So meanwhile, you type if you have any questions in chat box. I will take it. Yeah. This is the so in convolution, very simple. Just a few lines code we will write it. So it's very slow. Yeah. So so just to see, I'm loading the data set I stored in the drive. So I'm importing my drive. Okay. So how I'm importing drive, mounting my drive.mount we are doing. So here we can see. So here nothing is there. After it will run. Yeah, connect to particular drive. So I'm connecting to this mail ID drive. Continue. Mounting drive. This is where we can panel where we can upload data sets, everything. We can mount a drive also. The data comes here. Yeah, my drive mounted. See, my drive mounted. Okay. So now these are the packages in Python. So like NumPy, Pandas, so many things. So important one is model. We need to import a sequential model, dense layers, dropout, flatten, LSTM. Now we will discuss that later. Convolution 1Ds, convolution 2Ds, everything we will take it. So convolution 1D, wherever whatever required. Batch normalization, another concept is there. I'll discuss later. HGD optimization. So early stopping mechanism is other. So I'll simply run this. Next, we are converting that DNA sequences into one hat encoding vector. You see, if this is the DNA sequence, how it will convert into one hat encoding vector. Yeah, this is the one hat encoding vector. Now I'll take batch size 1000. Batch size is, we will not send all input at a time. So 1000 we will send it. Number of epochs 50 times we did. Binary classification. Number of classes are 2. Okay. So from here I collected my data set. So I'll running this. I'm converting into one hat encoding vector. So this I'm calling one hat encoding vector. Class labels I'm storing in somewhere in labels vector. So total 2648 what are there? That samples are there. Now this is the model. See, you should understand what is CNN. So model equal to sequential. This is a sequential model. Convolution pooling like this. It is performing. So input shape is 90 by 5 length. We converted. Convolution 1D. Filters 32 filters. Kernel size 7. Strides 1. Activation ReLU. Kernel initializer randomly. So initializer random uniformly. The kernel values randomly will inform. We will initialize. So 5 by 5 means 25 values for each kernel. By those 25 values, it will follow random uniform. Padding equal to same. In the first layer, padding equal to same means same number of that convolved feature vector it will generate. Next, dropout 0.2. Max pooling 1D. Pool size is 2. Strides 2. 2 jumps it will do. And the next convolution, filter 8, kernel size, and so on. Stack of convolution pooling, we use it 3. Then flatten, we converted into. Then those 72 values we connected to 32 neurons. Now dropout 0.5, 50% of values we dropped. Predictions, dense, two predictions we are doing. Softmax. Softmax works for both binary and multi-class classification. So we are model equal to Keras model inputs and outputs. Okay, we want to perform. We are compiling the model with categorical cross entropy, Adam optimizer, accuracy metric, model summary, return model. Yeah, so I'm running this model. So AUC, ROC, AUCP curves are there, metrics to represent graphs. So AUC, ROC is false positive rate and true positive rate we can draw. And AUC PR is precision recall curve. It is. So we written code for that. So now you see my model is, I'm training my model. So X train, X test. I splitted my data set into train and test sets. So it is training. It's a very big code actually. I'll share with you people. You please explore everything. So see, if you see this model summary, initially 90 input is 90 by 5 length. Next one is 90 into 90 by 1 length vector 32. So next one is 45 after max pooling. Next convolution 42, 8 channels it will generate. So after max pooling 21. Next convolution 19. Yeah, everything summary we will get it. Total after flatten 72 new outputs we got it. We connected to 32 dense. Finally, it will connected to one 2-dimensional vector. So for 50 epochs we are doing. This is the accuracy, training loss. Every time training loss is reducing, accuracy is increasing, you see. So we did for what we did 10 class validation, we did it. Okay. So it is learning. See, for epoch, so this is fold 1. Okay, 10-fold cross validation, 0th fold, first fold. What is the F1 score, accuracy, everything we measured here. Now it will let it train. Okay. Now what are the problems in convolution neural networks? We will see now. Okay. So many in agriculture also we can use, like this is one simple example, potato leaf disease classification. So image, I'll take it, same type of CNN network I can use for various tasks. What are the advantages of convolution neural network? Okay. So the converter is able to successfully capture spatial and temporal dependencies. Spatial means spatially it will extract features. Temporal information also it will consider. The weights are number of weights are very small compared to MLP, and a more effective approach, and can go deeper and deeper. If you want if you want to extract complex features, you can increase number of convolution max pooling layers. Layers are sparsely connected rather than fully connected. So the weights are stored in the kernels, right? So the kernels values are very less. It is not like millions, okay, very less compared to MLP. What are the limitations of CNN? Every deep learning model, the limitation is black box in nature. They are extracting features. See, this model, if you take it, till now it is extracting features. Up to here, it is extracting features. Whatever the features, 72 features we got it, then by using those features, we are doing classification and prediction task. So 2 tasks it is doing. It is extracting features and it is performing classification and prediction task. But which features, that those 72, what are those 72 features? We don't know. Only we can see numbers. From that numbers, we come to understand which features it is extracted. From image, which shape it extracted. So from DNA sequence, which pattern it extracted, we don't know. And long-term dependency problem. CNN can't remember previous information. So to overcome this long-term dependency problem, recurrent neural networks, we are going to use it. And to overcome this black box nature, we will do what we can do. We can use interpretability and explainability. Okay. These 2 solutions are there. For black box nature, we use interpretability or explainability. For long-term dependency problem, we will go for a recurrent neural network. So this is about the session, because I explained very fast, so many topics. So I'm on time, 7:25. So 5 minutes. If you have questions, we will address those questions. Please type in chat box. Now you come here, that model, model trained. So finally, after 10 epochs, this is AEC ROC curve and AEC PR curve. So these are the average AEC PR, ROC value, AEC PR values. Okay. So next is questions. Here are some questions. How many hidden layers we will consider? So that number of hidden layers, filter size, kernel size, number of kernels, like hyperparameter, like that eta, learning rate in MLP, all these are hyperparameters. So we need to tune hyperparameter tuning technique. So we need to select number of hidden layers. So number of hidden layers, there is a research area like neural optimal architecture search. So that by using that neural optimal architecture search, we will identify number of hidden layers. Due to network issues, several times exited and needs to be rejoining. That is not my problem. Please, organizers, please take care. How should medical imaging data sets to be structured? So actually, for medical image analysis, we need some images, medical images. Okay. So that you just go through literature, different papers, they will give you links for medical images. So, and so we can change the size of images. Suppose input images are various lengths. we can doing padding, we can make it fixed size. That we can do. Balancing storage efficiency, meta integrity, disk IO performance, and GPU utilization. So yeah, so many, each and everything is very like big CNN training. So through backpropagation we can update, balancing, all these are various tasks. Okay, so we can use different CNN for different medical images. And the next one, yeah, that's the question. uh, Last 2 minutes, if you have any questions, please. Otherwise, tomorrow after this session, another session is there. Tomorrow 2 p.m. we will meet once again to address the challenge of long-term dependency problem. Okay, so that's it. Thank you very much. I pushed a lot of information. Please, you have to revise it. Okay, thank you very much.
Thank you, sir. Thank you, sir.
Yeah.
Uh, hello, sir. Ma'am,
Yeah.
Vasanta, ma'am,
Yes, sir. Yes.
are you ready, ma'am?
Yes, sir.
Please
Yes.
give vote of thanks, ma'am.
Okay, sir. Okay.
Now
Thank,
I'm quitting.
Sir, wait for 1 minute, sir, please.
Okay. Okay.
sir.
Okay.
Thank you, sir. What you said, that is right. You have put a lot of information towards us, and it has been a truly insightful session today. And I take this opportunity to express my heartfelt thanks to our speaker, Dr. Chandramohan, sir, for invaluable knowledge on convolutional neural network. Your in-depth explanation of activation functions and the most popular types of activation functions like sigmoid, tanh, and ReLU activation functions, and backward propagation, and the need of weight updation in the neural networks, and the components like convolution, padding, strides, and the pooling operations. And you have explained the architecture of CNN in depth. That was very useful for us, and the practical examples and real world applications you shared have not only clarified complex
ఆమెకు నోరు ఉందా చెప్పడానికి చిన్న పాప మాట్లాడడం రాదు
Yeah, I think you muted, ma'am. Vasanta, ma'am. Thank you, ma'am. Thank you all
Thank
for
you,
your
sir.
patience.
Thank you so much. Thank you so much,
Yeah,
sir, for sharing your valuable insights. Thank you.
thank you, ma'am. Thank you very much, participants. We'll meet once again tomorrow 2 p.m. I'll
Yes.
share, somebody send PPT. I'll share PPT and code with the organizers. They'll share with you. Okay. Thank you very much.
Thank you, sir. Thank
Thank
you,
you, sir.
Yeah.
Dear participant, next session will start within 2 minutes. Hello, good evening, Raju sir.
Yeah, good evening, Andy.
Good evening, sir. Ma'am, Vasanta ma'am,
Sir, yes, sir.
please could you introduce this Raju
Okay, sure, sir. Sure. Thank you, sir. Respected participants, welcome to the 10th session of this FTP. It is my privilege to introduce our esteemed speaker of this session, Dr. E. Raju Garu. Sir is a distinguished professor with extensive expertise in data mining, artificial intelligence, and machine learning. Sir holds his PhD and MTech from Usmania University and has made significant contributions to research through numerous publications in peer reviewed journals and international conferences. As a recognized academic and researcher, Sir has reviewed papers. Sir has delivered expert talks in AICTE sponsored short term training programs and faculty development programs. Sir's research interests include machine learning, deep learning, generative AI, making him a valuable resource in advancing AI driven innovations. Without further ado, let's extend a warm welcome to Dr. E. Raju sir to share his valuable knowledge. Thank you, sir. Welcome, sir.
Yeah, thank you, madam. Yeah, am I audible?
Yes, sir.
Yeah. Yeah, good evening, all.
Good evening,
Good
sir.
evening, sir.
Yeah, let me share my screen. Okay, so give me a second. Yeah, is it visible screen?
Yes, sir.
Participants? Yeah, is my screen visible?
Yes, sir.
Okay, then. Thank you. So, good evening, all the participants and organizers. I welcome you
Okay.
all to this AICTE 1 week faculty development program on advancements in AI and machine learning for modern engineering solutions. Okay, so organized by esteemed University College of Engineering, KU Kottagudam. Okay, so in today's session, I would like to discuss on the topic generative adversarial networks. In short, we call them as GANs. Okay, so this is one of my favorite machine learning algorithms, and I am very much excited. Are you?
Yes, sir.
Type yes if you are interested to learn this topic. I try to establish the basics of this GANs today in this session. Participants, type yes, yes. Yeah. Right. Thank you. So these 3-4 days, you might have studied about various machine learning and deep learning algorithms. Okay. So in machine learning, generally what we do, we take an input training set, and then we feed this into a model, and this model processes our input data and produces the output. Okay, so generally machine learning we use to perform a prediction kind of a task and classification kind of task. Okay, so it predicts and gives its result in the form of a output. Okay, then we compare this output with the expected output. So why we compare? To calculate the loss here. Okay, so with the loss, we'll try to update our model. Okay, so that our model performs better. Okay, so initially, if your this produced output and expected output, or generated output and predicted output, you can call them, and expected output, if both are not same, then we calculate and we try to update the model. Okay, so that our model performs better and better. Okay, so this goes on iterating will this process until our model performs better. Okay, so this is simply a supervised learning in machine learning. Okay, so hope you might have studied this. Okay, but our GANs, okay, so our GANs are unsupervised. Okay, so we will try to understand why they are unsupervised at the end of this session. Okay, so but time being, you remember that our GANs are unsupervised. Okay, yeah, so can you just see these images? Say yes or no.
Yes, sir.
Yeah, okay, this this okay. So if you want, I share addresses of these professors at the end of this session. If you are interested, would you like to know their addresses? Say yes or no. Say yes or no. I'm not getting you. Okay,
Yes,
so
sir.
maybe
Yes,
in
sir.
chat. Yeah. Okay, right. Okay, so but these persons are not real, they are fake. Okay, so that means these persons does not exist.
AI
They are all
generated.
generated. They are all generated by our GANs. Okay, so that means essentially our GAN is going to generate a fake data. That is the basic funda in GANs. Try to remember this. Okay, so these persons does not exist. Please remember. Okay, so just you can see, you can generate images of persons who does not exist. Yes, you can go through a small video. Okay, so all these persons does not exist. They are all fake and generated by our GANs. Okay, so we'll try to understand the concepts of GANs in this lecture. Okay, so GANs is the most exciting idea in the last 10 years in machine learning. Okay, so this is the statement by Jan LeCun. Okay, so he is vice president and chief AI scientist at Meta. Okay, so he has given this statement. Then you can understand how important GANs are these days. Okay, so if you don't learn or understand the concepts of these GANs, okay, so you can just imagine how you will be going back. Okay, so while learning this artificial intelligence. Okay, so this is one of the important concepts of Gen AI. Okay, so another important application of GANs, I'll just give you some idea. Okay, so I have a source A with some images and I have source B of this person image. Okay, so then I can combine the result of A and the result of B, then I can generate these kind of images here. Okay, so these are all the images of persons who are not existing. Okay, so this is one of the application of GANs. Blending you can do, and you can generate new fake images of persons. Okay, right. So we'll try to understand what exactly are GANs, generative adversarial networks. Okay, so in this today's lecture, okay, so my presentation starts with what are adversarial generative adversarial networks, GANs. Okay, so we'll try to understand the concept. Then we'll talk about generator, what is generator and what is discriminator. Okay, then how GANs exactly work. We'll try to understand the working principle of GANs, and then we'll see what are the different types of GANs. Okay, then what are the applications of GANs. Then at the end, we'll try to implement GANs using Python. Okay, so without implementation, if you just learn the concepts, then there is no use. Okay, so that's why we'll try to implement these GANs using the Python. Okay, so first we'll understand what are GANs. Okay, so these GANs are developed by Ian Goodfellow in the year 2014 in the month of June. Okay, so this person has developed these GANs. Okay, so this person, Ian Goodfellow, got an idea. Okay, so what is that idea? Say, for example, he has 1,000 images of a persons with him. Okay, so 1,000 images are available with him. Then he want a machine, okay, or an algorithm or a program, okay, so which should learn from these 1,000 images and generate a image which is not existing. Okay, so you want to create, assume that these 1,000 images, it can be images of human beings, or it can be images of cats, it can be images of tigers, dogs, any. Okay, okay, so I want a program, okay, so which learns from these 1,000 images and generate a new image which is not present in these 1,000. Okay, so that is the basic idea he got, and then he developed the concept called as a generative adversarial networks. Okay, so all is we are doing in this GANs is we are trying to generate a new data here. Okay, we are trying to generate a new data that is not existing. Okay, so that's why the term generative. Okay, so we'll establish the concept here. Okay, so we understand each term here, what is generative, what is adversarial, and what is network. Okay, so generative means which generates data. Okay, so essentially this creates a fake data. Okay, that means the data that is not existing previously. Okay, so it creates fake data. Then assume here is an image. Okay, image of Mona Lisa which is not existing. Okay, so this is a fake image created by a GAN. Okay, so fake image, what kind of fake image? It generates fake image that looks realistic. Okay, so if you look at the image, then people understand that this is a realistic image of a Mona Lisa. Okay, but it is generated by a GAN. Okay, but it is a fake image. Then what do you mean by adversarial? Okay, so that means there are two components in this network. Okay, so one is called as a generator and other one is called as a discriminator. Okay, and each competing to win the game. Okay, so both fight with each other and both try to win in this game. That's why they play an adversary game here. Okay, so one is called generator, the component, and the other component is called as a discriminator. Okay, so that's why the name adversarial. Okay, so here what are these generator and discriminators? Okay, so they are, discriminator is a machine learning algorithm. Okay, so which classifies, or you can say discriminates a dog as dog or cat as cat. That's why the name discriminator, which discriminates an image. Okay, assume a dog image, it says as dog, a cat image, it says as a cat. It discriminates. Okay, so that's why we used the name, or the author used the name called as a discriminator. Whereas the generator is also a machine learning algorithm. Essentially, both these, the discriminator and the generators, both are neural networks here. Okay, right? So this generator trying to fake, okay, so create fake data, and discriminator always trying to not to be fooled by this generator. Okay, so that means what they do is assume this is generator and this is discriminator. Okay, so this generator creates fake data, okay, and passes it to discriminator, and discriminator tries to identify this data, whether this data is real or fake, and it says that no, this is fake data. Okay, so that means this generator creates a fake data and tries to fool the discriminator. Okay, so give the discriminator an impression that the data, whatever data it has created, is not fake, it is real. Okay, but discriminator is well enough to distinguish the data. Okay, so then it says fake. Okay, so they play this game again and again. That means it goes on, the game goes on, and there reaches a point where generator generates an image and passes it to the discriminator. Okay, then the discriminator says that this is a real image. Okay, so that means the generator has fooled this discriminator. Okay, so there ends the point. Okay, this is the funda of a GANs. Okay, so network means it is nothing but a neural network. Both a generator and discriminator, both are neural networks. Okay, so we implement both these two components by using a neural networks. Okay, so this is generative adversarial network. Okay, understood? Yes, say yes or no. Yes, Shravan Reddy. Okay. Ahmad, yes. Vanishri, yes. Okay. Right. Okay, then thank you. Now we'll try to understand the definition. I took this definition from Wikipedia. Okay, this is not my own definition. So what do you mean by generative adversarial networks? Okay, so generative adversarial networks are a class of AI algorithms used in unsupervised machine learning. Okay, so I said it is unsupervised. Okay, why it is unsupervised? Okay, because there is no classification or prediction kind of thing. Okay, so all we are doing in GANs is we are trying to generate new data. Okay, we are trying to generate a new data from existing or from random data or from noise. Okay, so that means there is no kind of classification or clustering kind of thing. Okay, so that's why it is called unsupervised. Okay, it is not a supervised classification kind of thing. That is supervised. Okay, prediction or classification. Now it is purely about generating the new data. Okay, so we are generating the new data, that's why it comes under unsupervised machine learning. Okay, so it is unsupervised machine learning implemented by a system of two neural networks. As I said, we use two neural networks, one is generator and the other one is discriminator, and these two neural networks contesting with each other in a zero sum game framework. Okay, so generally in a zero sum game framework there is a winner and there is a loser. Okay, so the profit obtained by winner and the loss incurred to the loser, if you sum up these, then that results into zero. Okay, so that's why it is called as a zero sum game framework. Okay, so this is the definition given by Wikipedia. Okay, so it is essentially an unsupervised machine learning and implemented by two components or two neural networks, you can say. Okay, so which compete with each other to win in the game. So as I said, GANs consist of a pair of neural networks that fight with each other. Okay, so one is called generator and the other one is called neural discriminator. Okay, so generator, we use a neural network to implement the generator, and similarly for discriminator also we use a neural network and we implement this discriminator component. Okay, so both are neural networks. Two neural networks compete with each other in this GANs. Now, how GANs work? Okay, so how they fight each other? Okay, so now this is a generator. Okay, so you can think of a generator as a counterfeiter who always tries to fake. Okay, so then you can think of the discriminator as a detective. Okay, so he detects whether an image is real or fake. Okay, so this game, these two play with each other. Okay, so that is called adversarial. Okay, right. So what this generator wants to print, assume that he wants to print some fake money. Okay, and this discriminator, he wants to distinguish whether the money is fake or a real. Okay, so whether the money generated from this generator is a fake money or real money. Okay, so that is the job of this discriminator. Okay, so during the training process, what this generator will do is initially he generates a bad image of a, assume that $100 note. Okay, and then he passes this to the discriminator. Okay, so then discriminator examines, okay, this $100 note, and initially, since it is a noise, he initially identifies easily and says that whatever you generated is fake. Okay, so then he gives this information to the generator. Okay, so this is fake. Okay, so then that means always the job of generator is to fool the discriminator. Okay, he wants to generate a fake money so that the discriminator understands that it is real money. Okay, so initially he starts with some noise. Okay, so he is unable to generate exactly a $100 note. Okay, so a noise image he discriminator gets, and the discriminator easily says that it is a fake notes. Okay, so then in the training process he learns from the feedback from the discriminator and he improves. Okay, so he updates himself, this generator, and he tries to generate more realistic $100 note. Okay, but still there are some unwanted okay, so images or some text in this note. You can just identify this. Okay, so then he supplies this to the discriminator. Then the discriminator again examines, because already the discriminator is trained. Okay, he is trained with a real 100 note, okay, and a fake $100 note. Okay, so that's why he has already has the knowledge of which is real and which is fake. Okay, so then he examines the $100 note supplied by the generator. Okay, then he examines the actual one also. Okay, so then again he says that this is a fake. This is a fake. Okay, so then again the feedback is given back to the generator. Okay, so generator again improves himself, updates himself, and at some point of time during the training he generates a note, a fake note which looks a realistic $100 note. Okay, then this is given to the discriminator. Okay, so then the discriminator examines both the $100 supplied by the generator and the actual $100 note. Okay, so both look same, and he will be in dilemma which is a correct one. Okay, so he examines both of them and he will be in dilemma. Okay, and finally he comes to a conclusion that this is the real note and this is the fake note. Okay, so at this point we can say that the generator has fooled the discriminator. Okay, so then the job of generator is done here. Okay, so that means he has generated a fake note which looks realistic, Okay, so then you can take this generator and now you can generate images. Okay, images of these which can be used for further processing. Okay, so this is how the GANs play the game. This is how the GANs work. Any doubts? No?
No, sir. No doubts.
Yeah, okay then. Okay then. Thank you. No issue. Okay. So this is the game played between a generator and a discriminator. Okay. So the task of generator is always to fool the discriminator. Okay. So initially he may not fool the discriminator, but as the training goes on, okay, and he reaches to a point where he generates a fake data or fake note which looks realistic, so that the discriminator is unable to discriminate which is fake and which is real. And ultimately he says that the data generated by generator is the real one. Okay, so that means he got fooled by the generator, we can say. Okay, right. So let us quickly understand the architecture of GAN. Okay, so initially the generator starts with some random noise. We call it as noise seed or latent vector, okay, of size 100. Okay, so you can take a latent vector of 100 values here. Okay, so then this we feed to the generator. Okay, and the generator generates an image. Okay, for each latent vector, it generates one fake image. Okay, so then these are the fake images. Okay, so for each one vector, one latent vector, one image. Okay, like this, it generates a group of fake images. Okay, then we also have a domain, our own domain containing the real images. Okay, so then what we do is we feed both fake images and real images to the discriminator. Okay, so 50-50, we take 50% of fake images and 50% of real images, then we'll feed to the discriminator, because the discriminator should understand which is a real and which is a fake. Okay, so that's why it should be trained with both real images and initially fake images. Okay, so then it gets trained and it tries to find out whether, and says that whether the image is real or a fake. Okay, so the output from the discriminator is whether the image supplied to this discriminator is real image or fake image. Okay, right. So what happens? Sometimes the discriminator may not give 100% that the image is real. Okay, so then there will be some loss. Okay, say for example 90% it says that the image is real image. Okay, so then we calculate the loss for the discriminator, and similarly we also calculate the loss for a generator. Okay, because generator is trying to generate a fake image. Okay, so but which has to be treated as a real image by the discriminator. Okay, so that means it is trying to send a fake image, and here it is detected as a fake only. Okay, so that's why there is a loss, we can say generator loss. Both for discriminator and generator, we calculate the loss and we'll feed this loss back to the discriminator, so that the discriminator improves, okay, updates its weight and improves. Okay, so hope you might have studied back propagation neural network algorithm. Okay, so the same happens here in GANs. Okay, similarly the generator loss also we feedback to the generator, so that it improves and it tries to generate a image, fake image, which looks like a real image. Okay, so this is the architecture of a GAN. Okay, so this is how this GANs work. Right. So the training goal for the generator is to maximize the probability of the discriminator making a mistake. Okay, so it always see that the discriminator makes a mistake. That means it is generating fake image. Okay, so whether the discriminator says whether this fake image is a real. Okay, so until it says real, then the training of generator goes on. Okay, so that's why it maximizes the probability of the discriminator making a mistake. And the goal, training goal of discriminator is to maximize the probability of identifying the real versus fake images correctly. Okay, so it should say a real image as real and a fake image as a fake. Okay, so that is the training goal of this discriminator. That's why we feedback this discriminator loss back to the discriminator. Okay, so like this, these two fight with each other until the generator fools the discriminator. So essentially, you can say that a discriminator is a binary classifier. Okay, because ultimately, what is the output from the discriminator? It says either a image is real or a fake. Okay, so that means either 1 or a 0. The output from the discriminator is either 1 or 0. 1 indicates real, 0 indicates a fake. Okay, so it's nothing but a binary classification. Okay, so you can implement discriminator as a simple binary classifier here. Okay. So quickly, I'll give the loss function. Okay, so we don't go deep into the mathematics. Okay, so this is the loss function given in the GAN paper. Okay, so I took this from paper containing this GANs. Okay, so discriminator is fed both kind of data. Okay, so this is d of x. Here x is the real data. Okay, so here x is real data here. Okay, so what is the probability of the discriminator, okay, saying that the real data is real? Okay, so that is the function given here. Okay, so then similarly, this g of this z indicates that the latent vector here. Okay, x indicates real data and z real data means nothing but it is a image here. Okay, so real images, as we have seen from the previous this real images will feed into this one. Okay, so this is x term here. Okay, right. And this z is nothing but your latent vector. Okay, so g of z is probability of generating this, and this is the generator function. Okay, so z is random noise. Okay, so then what is the this indicates a fake image here. Okay, so g of z of I indicates fake image. So what is the probability of the discriminator saying that a fake image is a fake? Okay, so this is the equation for this, because in previous slide we have seen that discriminator gets okay, so of real images and of fake images. Okay, so that means it should say a real image as real. What is the probability of saying a real image as real? Okay, so this is the function, loss function. Okay, so that means if it says only 90%, okay, so 90% correctly it says that this is a real image, this is a real image. Okay, so then there is some 10% loss that is calculated here. And similarly for a fake, this is the function. Okay, so that calculates the loss, okay, for saying a fake image as a fake. Okay, so 100% it may not say that a fake image is fake. Okay, so initially it may say that 70% it is a fake image, so then there is a loss. We say that loss is calculated here. This is the loss function. Okay, so it should calculate loss for both real and fake. Okay, right. Then now we have the question, does the discriminator want to maximize or minimize this function? Any guesses? Okay, so here the correct answer is maximize. Okay, so it wants to maximize this function. Okay, so you can go through that paper in GAN. Okay, mathematics, everything is given. Okay, then this is the generator loss function. Okay, this is log of 1 minus d of g, as we said. Okay, so this is a fake image. What is the probability of discriminator saying that a fake image is fake? Okay, so but generator always wants to say that it is a real image. Okay, it wants to fool the discriminator. Okay, so it wants to create a or fool the discriminator that it is a real image. Okay, so then there is a loss incurred here. This is the function, loss function for the generator. Okay, so for both the discriminator and generator we calculate loss, and here the generator want to maximize or minimize. That means it is always want to minimize this loss here. Okay, so because it want to fool the discriminator. Okay, so putting together these two functions, both this generator and discriminator play a min-max game. Okay, both of these two play a min-max game. This generator always wants to minimize this function, and whereas discriminator always wants to maximize this. Okay, so in min-max game there are two players actually. Okay, so what is the min-max game? Generally in min-max game there are two players. One player wants to maximize the probability, he wants to maximize the probability of winning the game. Okay, whereas the other person, okay, other person wants to minimize the probability of winning this game. The other player wants to minimize the probability of this first person winning this game. Okay, so this is the generally in min-max game played. Okay, so that is how mathematically this is expression min-max, and we have a value function where we have the loss generated by the discriminator and loss generated by the generator. Okay, so both will be given to this value function, and this is the expression. Okay, so those who are interested to go deep into these mathematics, okay, so they can read the paper on GANs. Okay, so it is given, taken from the GAN paper. Okay, so right, so how to train the GANs? Okay, so in the first step what we do is we define architecture based on our application. We'll see the applications. Okay, then we train the discriminator first. Okay, so to distinguish whether a image is real or a fake or data, you can say. Essentially we take a image here, image data. Okay, so a given data is real data or fake data. Okay, that means first we train the discriminator both on real data and fake data. Okay, so that it should understand okay, which is real and which is a fake. It should get the knowledge of a real and a fake. Okay, so that's why initially we train this discriminator with both these data, real data and fake data. Okay, so once it gets trained, then we train the generator to fake data. Okay, so that it can fool the discriminator. Okay, so we go on train so that it fake the discriminator. That means it can fool the discriminator. Okay, so it makes the discriminator to say that the data generated by this generator is real. Okay, so that's how it wants to fool the discriminator. Then you need to continue this training of a discriminator and a generator. Okay, so both multiple epochs will take, okay, 100 epochs or 200 epochs. Okay, so based on the quality of output, you increase the number of epochs. Okay, then you train both the generator and discriminator. Okay, so once the generator fools the discriminator, when you reach that point, okay, so then you can save this generator model, then you can create new realistic fake data. Okay, so that it can fool discriminator and also human beings. Okay, so this is how we create a GAN. Okay, so this is how we start with the architecture of GAN. Okay, so training the discriminator first, then training the generator, then we combine both of them. Okay, then we train both of them simultaneously. Okay, so that at some point the generator fools the discriminator. Okay, so then we are done with that, and we save that generator model to create a new fake data. Okay, right. So we'll quickly see what are different types of GANs. Okay, so we have vanilla GANs, and these are the simplest type of GANs where both the generator and discriminator are just like a multi-layer perceptrons implemented for simple kind of tasks. You can use these vanilla GANs. Then we have DC GANs, deep convolutional GANs, okay, which comprise convolutional neural networks here. Okay, and these are more stable and higher quality images if you want to generate. Okay, so then we use these DC GANs. Then we have conditional GANs. Okay, so if you want to add some extra information while generating a fake data, then you can use these conditional GANs. Say for example, you have an image. Okay, so you have an image. Okay, so this image you want to add actual original image, but you want to add create a fake image with some spectacles. Okay, in the original image there is no specs. Okay, but you want to create a specs to this image. Okay, so you can use these conditional GANs here. Okay.
Sir, please could
No
you?
voice, sir.
Hello, sir.
Sir, no voice.
Sir, Raju, sir, please could you unmute yourself, sir?
You turn down your mic, sir. Please turn on your mic.
Yeah, is it just now happened, or is it from the?
Just now, sir. Just now
now
happened.
only.
Yeah, yeah. Okay, yeah, I switched it to this screen now. Okay, maybe because of that. It's okay, right? Right. So we have SR GAN, super resolution GANs. Okay, so when we want to generate from low resolution image to high resolution image, okay, so then we can use these SR GANs. Okay, so what are the different applications of GANs? We will see quickly. Okay, so first one is if you want to generate a cartoon characters. Okay, like you have anime images, okay, used in cartoons, then you using those previous anime images, you can create a new fake images. Okay, so generally in cartoon kind of these kind of images, if they want to generate previously, there is a designer, or you can call a sketcher, okay, who sketches these images first. Okay, so he sketches these images, then using this sketcher, then they generate these kind of images. Okay, so that was the difficulty. But now if you have some cartoon images available, using these images, you can immediately using the DC GAN create a new Pokemon kind of characters or animation characters, new animation character immediately you can generate by using the GANs. Okay, then generating the human faces. Okay, so like this, you can generate faces of human beings who does not exist. Okay, so these are the persons who does not exist. Okay, so you can go to this website, okay, and you can get these. Okay, so let me quickly uh, open this. This person does not exist. Can you see my screen?
Yes, sir.
Yeah, okay, so you can just see here, these are the images of persons, okay, who does not exist. So if you refresh, then you'll get new images of so behind they are trained a GAN which generates these kind of images. Okay, so I took images from this website. That is okay, so generating a fake human faces. Then text to image translation. For example, I have a text like bird with a black head, yellow body, and a short beak. I want this kind of bird I want to create. Okay, so then if I give this text to a GAN, then immediately it generates a realistic image. Okay, so it creates a bird, and we feel that this kind of bird already existing. Okay, so this is one of the important applications of a GAN, realistic images from textual descriptions you can generate. Then the third one is, next one is 3D object generation. So if you provide two-dimensional images, okay, so then it can generate 3D models. Okay, so only thing is with the different perspectives, you give 2D images, then it generates a three-dimensional image for you. Okay, then image to image translation. Okay, so using conditional GANs, okay, there is a pix to pix conditional GAN already developed this model. Okay, so using that you can generate a image to image. Okay, assume that you have a real zebra image. Okay, so then this zebra image, okay, so you can generate a image that looks zebra looks like a horse. Okay, so image to image translation, and even you can reconstruct from the horse, you can reconstruct, okay, so it looks like a zebra. Okay, so image to image translation, you can just see here this small video I have. So it's a original horse video. Okay, now using a GAN, okay, so it is converted, this horse converted into a zebra kind of a animal. Okay, so that is image to image translation. Okay, then prediction of next frame in a video. For example, if you have these two frames from a video, then you can predict what is going to happen in the next frame. Okay, so even if you don't have these two frames, and you can generate these two frames using some GANs. Okay, so which is very much useful in surveillance kind of applications. Hope you understand. Okay, DVD GANs we'll use here. Okay, so using dual video discriminative GANs. Okay, so you can generate these kind of next frames in a video. Then low resolution to high resolution. For example, if I have a low resolution image like this, then I can generate a high resolution image without losing any information. Okay, so for this we use SR GANs. Okay, so even with finer details, you can generate a high resolution image. This is also very much useful in surveillance kind of applications. Okay, then interactive image generation. For example, you have a sketch. Okay, so then you can generate a realistic image. Okay, resembling this sketch. Okay, so like a semantic map to realistic images you can generate. Okay, or interactive, there is a GAN called as any cost GAN. Okay, so like interactively, you can generate new images. For example, this is the original image of the person. Okay, so then using a GAN, I have projected this image. Okay, so with finer details. Okay, so that it looks more and more fair. Okay, now you can edit this interactively, and you can create images whatever way you want. For example, I want to add a smile to this person. Okay, so then just by increasing this attribute, then I can add a smile to the person. Okay, then for example, I want the person to look younger. Okay, so then I can generate interactively, I can generate this. For example, I want to reduce mustache of this person. Okay, so then there is a attribute called mustache. Okay, if you reduce, you can see here. Okay, then I want to make this original image look older. Okay, so then you can just, there is an attribute called young. If you reduce or increase this, okay, with you can see black, you can change the hair color to gray color. Okay, so that means using any cost GAN interactively, you can generate images of a required kind here. Okay, right, say for example, a person original image, I want this person to wear glasses. I want a new image to create this kind with glasses. Okay, so all these are possible by using any cost GAN. Interactively, you can generate. Okay, so one application I'd show here. Okay, so image to image translation, there is a website called this. Okay, so let me just open this, and you can see image to image demo. Okay, so here you can just give a sketch here, then it gives a image, it generates an image of this kind. Okay, so you can clear, and you can even generate a cat of your own type. Okay, say for example, I want to draw a cat of this type. Okay, right, so I'm not good at drawing. Okay, so those who are good at drawing, okay, yeah, they can try this. Okay, so now if I say process, now it generates a fake image which looks like a cat of your sketch. Okay, so it takes some 1 or 2 minutes. Okay, so just let us wait. Similarly, meanwhile, we'll see other application. Now see, okay, so if you give different dimensions here. Okay, so whatever you want in a building. Okay, so then if you draw all of those with a window, door, wall, balcony, and all these, if you draw here, then it generates a building of this type here. Okay, it shows a building. If you give a sketch here, it gives. Similarly, see here for designers. Okay, they want to create a new style of shoes. Okay, so then it generates a new style shoe here. Just see here, bags. Even if you sketch a new kind of sketch here for a bag, then it generates how that bag looks like. Okay, so these are all image to image translations. Okay, so there is a website. Yeah, see now, see. So for this case, this is the kind of CAD generated by this GAN here, Pix to Pix GAN. Okay, right. So these are all different applications of GANs. Okay, so let us try to implement these GANs using Python, TensorFlow. Okay, so excited? Are you excited? Any doubts till now? Yeah, let me go back. Yeah, so I'll open Colab here. Okay. So the concept seems to be simple, okay, but implementation is very, very complex. Okay, so understanding the training process of the two neural networks when they are combined, okay, so is very complex unless you work on this. Okay, so I have taken a data set called as a Cypher. Okay, so I have taken Cypher data set here. Okay, so here first I am trying to load this Cypher 10, which contains images of different objects here, like a horse, okay, ship, a lorry, okay, frog. Okay, so it contains 10 classes of images. This data set contains. Okay, so now we will train a GAN such that we can generate these are all real images. Okay, so our GAN generates these kind of fake images, exactly like this. Okay, so that is the aim of this implementation. Okay, right. So here I have just included, and I am trying to load this, and I'll plot these images. Okay, so let me just quickly show this. I do not know whether I can finish the entire code or not. Otherwise, you can also load this code. I'll share this code. Okay, so this notebook I'll share. Okay, so you can load into Google Colab. Now see here. So Cypher 10 dataset is being loaded, and now a sample images, 49 images, 7x7 grid I have printed here. Okay, 7x7 grid I have printed these images. Okay, so
Sir,
then
if possible,
now,
please
yeah,
zoom it.
yeah,
Increase the
zoom.
size.
So if I zoom, yeah, can you see this now?
Yes, sir, guys. Thank you.
Okay, so just you can see the training data. That means that contains 50,000 images of size 32 by 32 by 3 images. Okay, so each image is of size 32 by 32. Okay, with 3 channels here. Total 50,000 images are there here. Okay, right. So this is a one sample image I have printed. First image, if I print here, see plain x of 0. Okay, so it looks like this. Okay, so if you reduce the size, you may get more clarity image here. Okay, right. So then what is the size of training data, test data, shape I am trying to print? See here, 50,000 total images. Okay, so test
Sir, could
size
you please
I have
repeat
taken
this
10,000.
part again? So please
Pardon?
repeat this part again. So please repeat this part again.
This one, training and
Yes,
test
sir.
one.
So the
Yeah,
from where you started on Google Colab training.
yeah, yeah. 1 second. Here I am trying to implement this GAN on a data set which is available in Keras, okay, Cypher 10, okay, so which is a data set containing 10 different objects images.
Sir,
Please
please
mute
put
yourself.
the,
Please, all of you, please mute yourself except speaker. Please, sir.
please. Sir, Raju sir, please could you unmute yourself, sir?
Yeah. So yeah, this is my Colab. Okay, right. Yeah, can you see this?
Yes, sir.
So yeah, this cipher data, initially I am loading this data, see load data. Okay, so I'm getting training and test data. I'm splitting this data into training and test data. Okay, so just I'm printing the first 49 images. Okay, just for your understanding how the images look like in this data set. Okay, the first 49 7x7 grid, I am trying to print this. Okay, so when I run this, I get these images. You can have understanding of these images. Okay, so then I am trying to print what is the size of training data, test data sizes. Okay, so you can just see here 50,000 in all original training data, 50,000 images are there. In test, I am taking 10,000. Okay, so each image is of size 32 by 32 by 3. Okay, so 32 rows, 32 columns, and 3 channels here, RGB, because they are colored images, RGB channels. Okay, right. So then you can just, okay, so train and test shape. Okay, right. So the first step is we need to define our discriminator. Okay, so our discriminator first need to be trained. Before that, we need to define the discriminator model. Okay, because it is a neural network. So here I'm taking a sequential here model. Okay, neural network. Then I'm first layer convolution network. Okay, so with 64 filters. Okay, so each 3 by 3 padding is same and input shape is 32. Okay, so 32 by 32 by 3 image. Okay, so ultimately what is the input to the discriminator? It is getting an image. Okay, so image, what is the size of image available in this data set? It is 32 by 32 by 3. Okay, so this is the input to this discriminator image. Okay, so then what I am doing, I am passing this image, then I am downsampling this image. Okay, so with 128 filters. Okay, so using, okay, so then I'll get an image of a, okay, right, so 16 by 16 image. Then again I am downsampling here. Okay, then again I am downsampling here, so 16 by 16. Then here if I downsample, then I'll get 8 by 8. Then again I am downsampling using convolutional networks, 4 by 4 image I'll get. Okay, so these are the layers I am adding to my discriminator neural network. Okay, right, so then finally I'm flattening the data here. Okay, so that because I'm getting here 32 by 32 by 3. Okay, so this is the data I'm getting. Then I am trying to convert that into a one-dimensional matrix here. Okay, or vector you can say, and I drop out, you know, how it drops some of the neurons so that the performance will be good. Okay, so at the final layer, I am adding a dense layer with one neuron here. Okay, I'm using the activation function as a sigmoid. Okay, because why the activation is sigmoid? Because ultimately the output from the discriminator is either 0 or 1. So the output from this sigmoid activation function from this layer will be either 0 or 1. Okay, so that's why in the last layer I'm using only one dense neuron I'm using here. Okay, so then I'm using the Adam optimizer here. Okay, so then I'm compiling the model. Okay, so with the binary class entropy, because discriminator is all about a binary classification problem. Okay, so I'm using binary cross entropy loss function and with the metrics as a accuracy. Okay, then it returns this model. Okay, so this is the function which defines our discriminator. Okay, so we'll try to define the discriminator model here. Okay, so now I'm calling the function, then I'm trying to create the discriminator model here. See, this function returns the, finally it returns this neural network. No, it is a neural network we have added here. 1, 2, 3, 4 layers of convolutions layers, and finally one dense layer. Okay, so this is our neural network. That model will be returned here. Okay, so now I'm calling the function which returns that model. This is nothing but our discriminator model. Okay, so just I'm printing the summary here. Then I'm trying to plot this discriminator. Okay, so how the convolution is happening here. Okay, so if you look at the summary, initially it is 32 by 32 by 3. Okay, so then that is using the 64 filters in the first layer. Okay, so then these are the number of parameters learned there. Okay, so then here I'm using a leaky ReLU function here. Okay, so this has nothing to do with in the training process. Okay, right? So it keeps the image size as it is. Then in the second one, then I am downsampling. So 32 becomes a 1616 with 128 filters here. Okay, so then leaky ReLU doesn't change the image size here. Okay, right? So then again in the next convolution layer, then I am downsampling. It downsamples to 8 by 8 with 128 filters. Okay, so again in the next sample I am downsampling it to 4 by 4. Okay, then finally now this is the final image 4 by 4 with 256 filters. Then I am flattening that, so it gives a vector of 4096. Okay, so some dropouts. Then finally in the last layer, so I am getting one neuron. Okay, so the output from this neuron will be either 0 or 1. This is the architecture of a discriminator. Okay, so implemented as a neural network here. Okay, so yeah, this is the diagram generated here. Okay, so let me just yeah, you can see. So initially 32 by 32 by 3. Okay, so then it is by using 64 filters first layer. Okay, so this defines the first layer. Then in the second convolution layer, it is downsample 1616 with 128 filters. Okay, so leaky ReLU nothing. Then 1616 is the input with 128 downsampled 8 by 8 you will get here. Okay, so then leaky ReLU nothing to do with that. In the next layer 8 by 8 to 4 by 4. Okay, so then finally then you are getting this 4 by 4 with 256 filters. I am flattening it this to single vector here. Okay, so in the final dense layer I have only one neuron. Okay, so this is my discriminator. Okay, so if I now if I give some inputs, okay, so real samples to this discriminator, let us see whether it says the image is real or not. For that I have defined a load real samples. Okay, so I have this data set load data, okay, which gives all the images into this variable train x. Okay, so then I am converting that into, because initially these images are unsigned integer types, I am converting them into floating point type. Okay, then their values will be 0 to 255 initially. Okay, so then I am rescaling it to -1 to 1, normalizing it to -1 to 1. Okay, so then finally I am returning that. After normalization I am returning that data here. Okay, so real samples. Okay, so now you can see here 50,000 real samples. Okay, it loads with the 32 by 3 size here. Okay, so now you can see x of 0, the first image, if I print all the values, previously it was 0 to 255, but now they are between -1 and 1. Okay, so if you print the image values, okay, so each pixel value, see each pixel is 3 channels, I said no, RGB values. Okay, so this is R and this is green and this is red, RGB, red, green and blue. Okay, so each pixel. Okay, and here this is from here to here, this is one row, this is one row here. Okay, so 32, like this we'll have 32 rows here, 32 rows. Okay, right. So that is I'm loading the samples here. Okay, so then I want to generate some number of samples. I don't want all the 50 images to be given. I want to train the discriminator in batches. Okay, so that's why I'm trying to generate the samples in batches here. So for example, 64 is my sample size, real image sample size. Okay, so basically, actually, what we do is to the discriminator. Okay, so we'll give both real data and we also pass fake data. Okay, so initially we pass as a batch of 128 images. Okay, so out of 128 images, 64 images will be real images and 64 images will be fake images. Okay, both these will be fed into this discriminator. Okay, so now I am trying to generate these 64 because I have total in my data set 50,000 samples available. Okay, so I am trying to generate the first 64 real images I want to generate. For that, I have defined this function. Okay, so this is the function defined for that. Okay, right? So yeah, so it takes another half an hour time. Organizers, let me know whether, because
Hello, sir. Sir,
yeah, because the code is very lengthy. Let me show the code. Okay,
Okay,
this
sir.
is how you should. Let me show the code. Okay, let me show the. Okay, so this is the code actually. Okay, so because you have so many things to discuss. Similarly, as here we are generating the real sample. Similarly, we need to generate the fake samples. Okay, then both we need to give to the. This is the fake image created. Okay, from 100 by 100. See, latent vector I said, no, 100 values latent vector if I take. Okay, so then this is the fake image initially created. Okay, as it gets trained, it becomes a image here, actual image. Okay, so then both the fake and the real, initially we need to train the discriminator. Okay, for all the 50,000 fake and after 50,000 real, so that it gets the knowledge which is fake and which is real. Okay, so this is the training for discriminator. It takes time. Okay, if I because it is computationally heavy GAN. Okay, please remember, GAN is computationally heavy. That means you require a heavy computational power. Okay, so heavy computational device you require. Basically, you need a GPU kind of machine. Okay, so otherwise in our machines it cannot be run. Okay, so I tried this, but for 24 hours and above, still for 200 epochs, I tried to run this GAN. Okay, so but since my machine is of a 16 GB. Okay, so even for whole night, it has not completed. Okay, all these epochs. Okay, so that's why you need a GPU. If you have a GPU, then you can see the results better. Okay. So what I do is, yeah, where is the code? Yeah, here Cypher. Yeah. So this is the code. Okay. So training of discriminator, then creating the generator model you need to define like this. Okay. Let me just walk through the code so that, okay, you can just, okay. So generator model you need to create. Okay. Then you need to generate fake images. Okay. This is how here in generator, in discriminator, we downsample. No, here we upsample. We'll start with small image because we need to create fake image. No, so we'll start with the 4x4 image and we'll try to generate a 32x32x3 image of fake image. Okay. So this is a training of a generator. Okay. Creating the fake images. Then after, then you need to generate fake samples. Okay. In batch, you need to generate 64 fake images you need to. For that, this is the function. Okay. So then initially, just you can see, initially it generates all gray images. If you enlarge this, you can find some noise. Okay, so in the first iteration, it generates these kind of grayscale fake images. Okay, now you need to define the GAN. That means you need to combine both a generator model and a discriminator model. Then you need to train. Okay, so then the competition starts. Then the competition starts, and finally, okay, so when you train this, now this is the function for training both this generator model and discriminator model. Okay, so and we also have a GAN model. Combined model is called GAN model. Okay, so we train this GAN model, and once we train this GAN model, now here I run the code here. Just see here. So this is the function, train function. Okay, so if I run this train function, I think I need to execute all the cells. Okay, because train I have not executed this cell. Okay, so like this I need to execute all the cells from the beginning. Okay, so then finally if I execute this function here, okay, so it starts training, because G model, all the cells I have not executed. No. Okay, so after even one epoch, your system gets hanged here. Okay, because of CPU kind of thing. Okay, so generally GAN requires a GPU kind of machine here. Okay, so once the final thing that is happening in this GAN is what happens, both generator model and discriminator model combined, that is called our GAN model. Okay, so then they start fighting with each other, competing with each other, and they reach a point. They reach to a point. I'll show. Okay. So both yeah. So just see here. So your discriminator and generator both combined and trained together. Okay, so now this is your GAN model when they combined. Okay, so both start generating fake images. It also gets a set of real images. Okay, so it tries to fool, and it reaches both gets trained here. Okay, so training happens 200 epochs, 300 epochs, or 500 epochs. Okay, so like this it repeats, and it reaches to a point where your generator generates a fake image, and ultimately this discriminator says that it is a real image. Okay, so it says that this fake image is a real image. That means it generates a fake image which looks realistic. Okay, it looks as if like a real image. Okay, so there at that point, now the discriminator makes a mistake and says that it is real one. The fake image it says as a real one. Okay, so there ends the training, and now we save this generator model and we use this generator model. Okay, like other models. Okay, and now we can start creating a fake data which looks realistic. Like we have seen, this person does not exist.com. Okay, so this is the model that we want to create. Okay, so this is our GAN model ultimately. Okay, right. So let me just show the, yeah. Nice. We'll go back here. Yeah, these are the images. Okay, so let's just, after 10 epochs, these are the kind of images generated. Okay, then after 100 epochs, you can see more clarity images you are getting. After 200 epochs, because the code is for 200 epochs. Okay, so it gets still the image is not clear. Okay, so you can increase number of epochs so that you get better quality image. Okay, right. So thank you, one and all. Any doubts? I can take one or two doubts.
So please send the code.
Only
Yeah,
Only for image
code I'll share
generation?
with the organizers. Yep, pardon?
is it to use it for generation of only image data, or other data, audio or textual data can be generated using GAN?
Yes, there are so many applications I discussed, no, sir? Okay,
Okay.
even audio, if you train with audio, it can generate a new kind of audio which is not existing. Okay, so like for example, if you train a GAN with a different songs, okay, so then it generates a new song which is not existing. Okay, or for lyricists. Okay, so if the lyricist train with a different lyrics songs, okay, then if you ask the GAN to generate a new lyric, then it gives a new song. That is the power of GAN, sir. Okay,
Like
so I'll just,
yes.
pardon, I'll just show the there are 18 applications mentioned for these GANs. Okay, so it is going to occupy everywhere, sir, in future. We might have heard about Gen AI is going to replace all the musicians and lyricists. Okay, behind the Gen AI, it is nothing but the GAN only, sir. So machine learning mastery.com. Okay, so in this website, okay, so you can just go through for your understanding. Okay, 18 impressive applications of GANs you can just see here, sir. Yeah, so these are all applications. Yeah, so photographs of human faces. Okay, generate realistic photographs. Okay, like these birds kind of objects. Okay, so then cartoon kind of characters it can generate. Image to image translation. Okay, see, for example, this is the input image. Okay, so can you see this? Okay, so morning you want to see the same in the night. Okay, so you can just translate this. Okay, so this, then sketch to image. Okay,
Sir,
so
in that
then
sketch to image, how the
Yeah.
discriminator is going to identify like original? Original is one is the sketch, no, sir? Like
yes.
the generated one will be the real image. How the
No,
discriminator is
this
going
is
to,
this is real, sir. This is fake only. This is created only. This is
Okay.
created fake image. Okay, if you train the GAN, okay, so generator such that if you give a sketch image, ultimately it should generate a image of this type. Okay, here in our previous example, we want to generate
I
a
mean,
same kind of image. Okay,
Yes,
the
sir.
training is different in this case, sir. We use a
Okay,
different kind of GAN here. The kind
yeah,
of
where
training
in the
we
discriminator will have sketch as a image, sketched image as a real image, or the which one
both
generated as the
sir, discriminator always gets two kind of images, 50% fake and 50% real images. So with these kind of real images, we train the discriminator initially.
Okay, sir, understood. Thank you.
Getting, sir? Okay.
Yes.
Right. So these are all text to image translation. These are all applications. Yeah, just you can go through, sir. Okay. So all these 18. So this plays major roles are GANs in Gen AI. Okay, photo blending also you can do like this. You can just see here. So super resolution. All these are examples. Yeah, sir. So let me take a pause. Yeah, this one. This. Okay. So thank you one and all for your patience listening. Yeah, any more doubts or?
Does there exist tools to that will recognize like a GAN generated images are the fake real time tools?
GAN gen-
Like
Pardon,
GAN
sir?
generated images are kept on the website, sir. Real images are
Yeah.
also mixed with them. Are there any tools to recognize which are fake, which are original?
This person does not exist. This website, see, sir. Okay. So it
Yes,
seems
sir.
to be a human being image. Okay. But this person does not exist. It is generated by a GAN, sir.
Is there any tool to recognize this as a fake image?
This one, sir.
Usually these images are fake images. Will they be identified by some tool or something?
Yeah, that's what in Gen AI. Okay. So if you large language models, if you use, okay. So then there you can identify. Still research is going on. Okay. So which is fake image, generated image or real image. Okay. So in LLMs, we can apply these things. There you can identify, sir, whether it is AI generated or real image. Okay. So I don't know any tool which identifies this, sir, as of now. Okay. But if there are any tools, I'll let you know, sir.
Okay, sir. Thank you.
Sir, can we use these generated images in our research work?
Pardon?
Sir, can we use these AI generated images in our research work?
Yeah, still lot of research is going on GANs, ma'am. Okay, so you can take this is the basic thing we discussed today. Okay, so there is uh, so much work is going on using DC GAN, SR GANs. Okay, so if you read papers,
Yes,
then
sir.
you can establish one problem. You can use GAN. This is latest research area, madam.
Right, sir. Right. Thank you, sir.
Thank you, sir. Hello, sir.
Yeah,
Sri-
yeah, please.
Okay, thanks. Dear participant, do you have any doubts?
No, last doubt, sir. Sorry.
Okay. Okay, sir.
So, like if I am generating data using GAN for some my security application, like to generate the malicious data,
Yes, sir.
if can I use that
What for
data set as like I want
Yeah.
a model to distinguish between the benign data and malicious data. So the data will be generated with the GAN. Can
Then,
I
sir,
prefer this as a standard data set as we provide like Kaggle or something, or
yeah, that's what the major thing is in GAN. You should have proper data sets, sir. Initially, to train the discriminator. Okay, so we should have proper data sets so that it recognize the original data as real data as real. Okay, so if you don't train the discriminator properly, and if you directly feed fake data generated from this generator, okay, so that may not be of that useful, sir.
okay.
So directly if we generate from the generator and ask the discriminator without training it much, then you may get fake kind of images which are not of that useful. Doesn't look realistic. That is.
Okay.
Understood, sir.
Excuse me, sir. Am I audible?
Pardon. Yes, sir.
Will have you suggest some research topic for this topic?
Yeah, you can, this is I found this machineLearningMastery.com, sir. Okay, so machine learning mastery, there is a topic called as a GANs. Okay, so all kinds of GANs with implementation they have mentioned here. Okay, so machine
Okay.
learning mastery,
Okay. Thank you.
machineLearningMastery.com, sir. Okay,
Please,
so
please.
you can
Thank you.
get, yeah, okay. Any other
Thank you.
doubts? Okay, then participants, thank you one and all.
Thank you, sir.
I thank.
Wait
thank-
for
Thank you.
Wait for one
Thank
minute. Vasanta, ma'am.
Sir, yes, sir.
Okay.
Sir, thank you so much, sir. It is my privilege to extend our heartfelt gratitude to Dr. E. Raju Garu for his enlightening talk on the fascinating topic GANs. Sir, your in-depth explanation of GANs, like how to GANs works and the steps of training a GAN architecture and the role of generator and discriminator types of GANs and the applications of GANs are very interesting, like generating human faces, text to image transitions, etc. And you have explained how to train the GAN model with a code is with an execution is very useful and informative as well as interesting. I would like to thank for taking the time to be with us today and for sharing your valuable insights. Thank you once again, sir. Thank you.
Thank you, madam.
Thank you, sir. A small announcement for the participants. Tomorrow session starts at 2 p.m. and after completion of 3 sessions, you have an online test. Which regarding that, we'll send the feedback as well as online test Google Forms. So please cooperate and try to attend the exam. Thank you. Thank you, one and all.
Thank you, sir.
Let's request ma'am, respected ma'am and sir, please share the PPTs and video recordings also.
So definitely we will send by tomorrow. So no, don't worry about your PPTs. We'll share all the PPTs as well as the video recordings to your individual mails.
Ma'am, if you send early, it will be easy for preparation, ma'am. That's why we are asking. Thank you
Yes,
so
sir.
much.
Yes. But it is difficult to share daily contents. That's why we are
So
sending the
tomorrow,
bulk of
yes, ma'am.
content. Yes.
So
Tomorrow,
otherwise, you can upload in a Google Drive, ma'am. No?
yes, sir. We'll
Then
upload
you
in Drive
can,
only.
yeah, you can.
Yeah.
Thank you, ma'am.
Definitely, sir. Definitely, we'll do that.
Excuse me, ma'am.
Yes, ma'am.
Ma'am, actually, will the exam will be held on only between 6:30 to 7:30 p.m.?
No, madam. From 7:30 up to 7:30, you have a session. Last session up to 7:30. After 7:30, you have a test.
After 7:30,
Sorry, 6:30 to 7:30. Yes, madam. 6:30 to 7:30. 1 hour duration. You have an online test.
The
this is the
exam
fixed
is
time.
it through Google Form or in our portal, Atal portal?
Google form only. We'll
Okay,
share the
ma'am.
Google form
Okay, ma'am. Thank you.
regarding the online test.
After
Excuse me,
7:30, we cannot avail the exam, ma'am.
Sorry, ma'am.
Excuse me, after 7:30,
Yes,
we
yes.
cannot
Yes,
avail
it
the
will be.
exam.
Yes, you are not supposed to attend
It
the
will be
exam.
closed.
Yes, madam.
excuse me, ma'am.
Yes, sir.
So, ma'am, when our attendance is updated in portal, ma'am.
Sir, we'll talk to our coordinator, sir, and we'll inform you very soon. After completion of your test only, you will get the certificate.
Hey, ma'am, it's okay. My question is when our attendance is updated on Atal portal.
Daily it is updating in Atal only, sir. Daily it is uploading, and the mail is sent to the same attendance will be shared to the coordinator also.
Ma'am, actually, my today problem is I attended all the sessions, but today due to
Okay.
network problem, I cannot able to attend the first session, ma'am.
Okay.
Due to network problem, ma'am.
Okay.
So, what is the solution of this, ma'am? I attended all the sessions previously.
No problem, sir. No problem.
Okay,
ma'am.
sir. We will check that all the attendance, sir. No problem. You won't get any kind of problems.
Okay, sir. Thank you.
Thank you, sir.